Okay, so let's get started. Last time we wanted to find the lowest energy field configuration of, or static field, approximately static, aside from the fast oscillations, field configuration of some complex scalar phi that has some fixed total charge Q. And we assumed that the potential of phi had this slightly unusual form where it had some dip below m squared phi squared, some intermediate field value being minimized at phi naught. We reduced the problem down to minimizing this curly E of omega, where omega is some new Lagrange multiplier. And then from that, we wanted to solve this differential equation, which gives the effectively field value as a function of the radius from the center of the object, with the boundary conditions just that the solution is smooth at the origin, and that as we go to spatial infinity, the field goes to zero, so that we have finite total charge. And I also told you that we could restrict to these values of the Lagrange multiplier. Okay, so first question is, does a solution exist to this? Maybe it is a bit early in the morning to be volunteering people to come up and solve it, but anyone manage or want to, has seen it before? Okay, so there is a solution, and this is a nice argument by Coleman that you will see in several different places. The first trick is to notice that these values of omega, what I effectively do is take my potential there, and because of the minus omega squared phi squared, I turn it into a potential of schematically this kind of form. In fact, if I have that omega is exactly equal to omega naught, then the potential would look something like this. Draw that better. With exactly two degenerate minima, this would be omega's very slightly larger than omega naught. And as I approach omega is equal to m, this first minimum here almost goes away. So see if Okay, so now this equation of motion, just like for the domain walls, corresponds to just Newton's law for a particle moving in and a particle moving not in this potential but with the inverted potential. You pick up a minus sign when interpreting it this way. And then picking, for example, this middle solution. I got the shape slightly wrong, but you get the idea. We want a particle that moves in this potential. It starts off stationary at some initial time because we're interpreting the radius as some time variable. It starts off somewhere here. And then we need the solution that just reaches this hilltop here and where it stays for infinitely long. Now I can prove that a solution exists just by words, basically, by some sort of continuity argument. So it's immediately obvious that I can find a solution in which this particle doesn't reach this hilltop. If I just started off at any location with negative potential energy, then we see that the term here is a friction term, so the particle will only lose energy via it. So this particle will just undershoot and it will never reach this point. Slightly harder, but not much harder, is to prove that I can find a solution that overshoots this maximum here. So suppose that I start infinitesimally close to this hilltop here. Now the crucial fact is that this is not quite like a normal friction term, but it's a friction term that has a time dependence via this 2 over r factor out the front. So provided I wait sufficiently long, this friction will become arbitrarily weak. And if I start sufficiently close to the hilltop here, the particle will just remain there for as long as I want. I get the friction as small as I want. And then when the particle does roll, it rolls without friction. And because this hilltop is higher than this one, of course it overshoots. Everything here is continuous, so at least to some sort of physics level of rigor, I'm okay to say that given that I've got a solution that overshoots, a solution that undershoots, there must be some solution in the middle where the particle starts off somewhere here, and it just makes it to the top of the hilltop where it stays, which is exactly the solution we want. And this is a prototype of the kind of bounce solution that you'll see also in vacuum decay and similar cases. Now, the other thing we need to do, if you remember, is also minimize epsilon of omega with respect to omega in order to impose the constraint. In some ways, actually, this is almost like straightforward. If we carry out this minimization, all that it's doing is picking out, for a given value of Q that we want, the solution that corresponds to that amount of charge. The non-trivial thing that we should actually check is that for any given Q that we want, there does indeed exist a field profile that we require that has the right amount of Q charge. I won't prove this because it's just some sort of exercise in real analysis and it's perhaps not the most physically insightful. Coleman as always has a proof of this. One limit that is actually quite interesting and is physically useful is what is called the thin wall limit, although with slightly misleading terminology there. So let me suppose that I want to create an object with very large Q. That means that I'm going to have to create an object, a field profile that stays well away from phi is equal to 0 for a long time in order to build up a field configuration with enough charge. And this is exactly the solution that I was talking about earlier, very close to this solution I was talking about here, where this hilltop is only slightly higher than this one, so I need to stay for a long time here and then just roll later. So this corresponds to omega is only slightly larger than omega naught. And in this case, my object looks something like this. So I have a large region where, call it phi naught, then surrounded by a thin shell, which corresponds to the time when the particle is rolling to the other hilltop, and then outside, of course, phi is equal to 0. Without too much work, you can prove that in this case the charge Q is equal to 2 omega naught, and then just the volume of the internal region, so 4/3 pi naught, where we have that r is the radius of this cubal. And likewise, with a bit of algebra, you can show that the total energy of the object is omega naught Q. And then plus additional terms that scale as the surface area of this cubal rather than the internal volume. The charge scales as the radius cubed, so in the large radius limit, this term is dominant. Yes. So phi 0 doesn't have to be a minimum, it just has to be this point that is the minimum of du by d squared u by d phi squared over phi squared But the crucial thing is once I subtract off omega squared, phi squared, necessarily because, well, we're also assuming the potential is bounded below, so that will mean that there is a hill top somewhere in this part of field space. Okay, now I can also at least give some plausibility argument for the stability of this object. We have, by assumption that, by construction, that omega naught is less than m. That means that the energy of the cue ball is indeed smaller than just n copies of individual quanta, or excitations around the vacuum. And in particular, if I lose a single charge 1 excitation from this cue ball, the total energy of the system would go up, so I've therefore got some stability. Maybe the final thing to comment is that also in the large charge limit, we have that the mass of the cue ball is large compared to the mass of the excitations around the vacuum. So actually our classical analysis is valid, and we can think of this as some classical object on which we build states in our Hilbert space. Okay, next natural question would be, what is the pheno of these types of objects? And this is perhaps a bit uncertain, and whether cue balls could play some role in the early universe is, I think, unknown and not particularly clear. So first of all, there's no scalars in the standard model that have appropriate properties to lead to cue balls. All we have is the Higgs, and this doesn't have an appropriate potential. You could imagine, if you know about supersymmetric models, there you of course have many more scalars, you have squarks, and so on. In these scenarios, glue balls can be possible in some, at least in some realizations of supersymmetry. Perhaps the problem or challenge there is that such cue balls are unstable usually to decays to fermions if they're charged under baryon number, decays to neutrinos if they're charged under lepton number, well, the leptons of course. People have constructed theories with stable or metastable cue balls and supersymmetric theories, but it's not immediate. You can also get formation in the early universe. Typically, the way this might happen is by something like Affleck-Dine baryogenesis, where some squark would get an extremely large expectation value in the early universe. This would then fragment into cue ball solutions. I think, taking into combination all the observational limits, it's pretty hard to make some cue ball in the standard model dark matter. You could always have some hidden sector theory with a hidden sector cue ball, and maybe there's some interesting pheno to be explored there, but I don't immediately know. On the other hand, as I said at the start, it's kind of an interesting warm-up example to see how these non-topological solitons work. Okay, so maybe before I move on to at least what to me would be maybe a more realistic example of such a soliton, are there any questions on this part? No. Okay, good. Okay, so now I'm going to talk about axion stars. These are similar non-topological solitons, but they're perhaps easier to realize in extensions of the standard model. So of course you're learning about axions with critique, but for my purposes I'm going to be a bit more general than just the QCD axion, and I'm going to allow an axion to be any light pseudoscalar. Just with the requirement that, for the sake of definitions, let me say that the mass of the axion is much less than an electron volt. These can very naturally arise from spontaneous breaking of some global symmetry. They can also occur from extra-dimensional models, as again you've seen, and so on. So typically we'll also assume some approximate shift symmetry, which is then a nice explanation for why the axion might be light. I'll again call the axion phi just to keep the notation standard. And I'll allow a small amount of shift symmetry breaking such that there's a small potential. Let me say V of phi is for the QCD axion, this quartic coupling is parametrically of the form ma squared over ma to the 4 over fa to the 4. Now, despite the fact that these axions are so light, they actually comprise a good dark matter candidate. You can't produce them by normal thermal production mechanisms because then they would be relativistic in the late universe and dramatically ruled out by observations of structure, for example. But if you've heard of misalignment production or similar, also production by topological defects, as we've discussed, then they can be perfectly good non-relativistic dark matter candidates. Maybe one of the most interesting features of axions as dark matter candidates is that their occupation number in the present day universe is absolutely huge. So by this I mean the number of particles per de Broglie wavelength, equivalently the occupation of each state. So if I put in numbers, this occupation number is roughly number density and then size of the de Broglie wavelength. Which turns out to be 10 to the 22, then normalizing the energy density to, let's say, roughly the local value, 0.4 GeV centimeter cubed. This means that in the local environment, to an excellent approximation, the axion field is incredibly classical. So we can just treat it as some classical wave that we solve in classical field theory. Okay, so now let me ask how this axion field evolves in the late universe. Since we know that the axion field is non-relativistic, it's a bit inconvenient to work directly with the relativistic field, and instead we can make a non-relativistic reduction by defining a new variable, I'll call it psi, by 1 over square root 2 m squared minus I mt plus complex conjugate. So I'm replacing phi with psi, and the trick in doing this is that I'm effectively factorizing out all of the fast oscillations of the field that are happening on timescales that are much shorter than any of the other dynamics that I'm interested in. In particular, in the limit that psi dot is much less than m psi, psi double dot much less than psi, then our original Lagrangian reduces down to these things which are not fast oscillating, and then plus a bunch of fast oscillating stuff that we can safely chuck away. You can see that psi is a complex field, so it has 2 degrees of freedom. On the other hand, that might look like some miscounting here. However, we've reduced down from a second order Lagrangian down to a first order one, so actually the number of degrees of freedom has stayed the same. And with a bit of staring at it, you can convince yourself that the number density of axions is up to some normalizations depending on m that are just the absolute value of psi. The thing that is missing from what I've written so far is gravity, and of course we're going to be interested in how these axions evolve in the universe when gravity is suddenly relevant. I can include this by putting in accounting for a Hamiltonian that is minus g mass of the axion, then that turns out to be a factor of 2 when you're careful about the normalizations. d cubed x prime psi star of x. So of x, so this is effectively the axion number density at one point, then coupled to the axion number density at the point x prime. And with the denominator that you'd expect for the gravitational interaction. Now, if you combine this interaction with this starting Lagrangian, you can work out your equation of motion. And after all this, you get just what looks like a very simple equation of motion. So the first part just looks like a normal Schrodinger equation, but then we have some interactions. The first part just looks like, as I say, a Schrodinger equation, but now with some more complicated interactions. And with the addition of this term capital phi, which is the gravitational potential obtained by solving Poisson's equation, as you would kind of plausibly guess. Now, the reason that, well, one of the reasons that non-topological solitons are interesting, and also actually that axions have a chance of being an interesting dark matter candidate, is that to first order in lambda, there are no number changing interactions for psi, and actually in realistic theories, for example, QCD axion, the quartic coupling is going to be tiny anyway. So on kinematical grounds, we can't have 1 to 3 interactions. Likewise, 3 to 1 are forbidden. And the leading order number changing interactions would be order lambda squared in the, at least in the amplitude. This means that to an excellent approximation, the total axion number is conserved. Okay, any questions about, yep. Yes, so here, if we go into the rest frame of the one that is coming out, then the kinematics won't work out. So I'd have to have 3 particles coming in with 3 times their mass, leading to one stationary particle coming out. Yeah, so it'd have to be like, I think the leading things would probably be usually you get sort of ladders of these kind of things leading to the first things where the kinematics actually work. Okay, good. Any other questions? Yep. Yep, so this is kind of just the translation of the Newtonian and Hamiltonian, take into account that this is the number density and the factors of mass are picked however they work out. But indeed, a good consistency check is that actually we should be in the Newtonian regime in order for this to work out. Otherwise, we'd have to do general relativity and harder. Good. Any other questions? Okay. So let me now look for solitons, axion stars. Now, so we want solutions of the Schrödinger-Poisson equations that minimize the total energy, but with a fixed axion number density, total axion number. So now instead of capital Q for our Q balls, we want to keep fixed phi, absolute value of psi squared. Given this, I don't know if it's completely standard, but I would call axion stars a non-topological soliton. These solutions are possible with attractive self-interactions in which the attraction is the thing that is binding the axion star together. They're also possible with repulsive self-interactions as long as these repulsive self-interactions are small enough compared to the gravitational interactions that the star can still be bound. But actually in realistic theories that I think have a chance of actually existing, usually the quartic coupling is completely negligible compared to gravity. So for our purposes, we're just going to forget about lambda, set lambda is equal to 0. Then the first important thing to note is that the Schrödinger-Poisson equations have a scaling symmetry. If I have some solution psi and I take this to alpha squared, let me write it in slightly more detail. If I have some solution psi as a function of time and position, and I take this to alpha squared psi alpha squared t alpha x, and also simultaneously start with capital phi and rescale this to alpha squared phi alpha squared t alpha of x, then the thing that I get out is still going to be a solution. This is nice because it means that if I can construct an axion star solution for one particular value of the mass, then I can connect this to axion star solutions with any other value of the mass that I want. I only need to solve my Schrödinger-Poisson equations once. I'm not sure if it's been rigorously proven, but given the discussion of Q balls, it's at least very plausible that the lowest mass state will have lowest energy state with a given mass will have spherical symmetry. Let me just take that as an ansatz. Let me look for solutions of the form psi is equal to some normalization factor. Let me just choose it to be m over 4 pi g. This is just to get the stuff that comes afterwards dimensionless. And since it's a Schrodinger-like equation, let me write e to the minus I gamma mt as my ansatz. And then a time-independent function, let me call it chi1. And to make this dimensionless function a function of some dimensionless argument, I just work in terms of the distance from the center of the star normalized by the axion mass. And similarly, I write phi is equal to phi1 of mass times radius. So here, again, just like the cue-ball solution, I'm thinking of r as being the distance away from the center of the object. Maybe one thing to comment is that if I go back from this non-relativistic field to the relativistic field, we're going to have that the relativistic field scales, varies with time as e to the I mt minus I gamma t. And if you look at this and you compare with how you expect fields usually to evolve, we can interpret gamma as being mt. As being some effective binding energy per unit mass of the axions. Anyway, aside from that, with these ansatz, we reduce the Schrodinger-Poisson equations down to ordinary differential equations. And moreover, we only actually need one solution because of our scaling symmetry. So because of that, we can just impose that our solution chi1 of r tends to 1 at the center of the star. And we want our axion star to have finite extent, so we want chi1 of r goes to 0 as r tends to infinity. And analogously, we're given this setup, we're going to impose that our gravitational potential, let me say, goes to constant 0. Okay, good. There's no exact analytic solution to these equations, but it's pretty straightforward if you put them on a computer just to find the solution directly. So with these boundary conditions, actually the solution has this number gamma is about minus 0.7. Depending on your sign conventions, let me put it plus there. And the field profile as a function of radius looks something like this. So this is chi. If you ever need some exact or some good analytic approximation, this central region goes as something like 1 plus 0.2 r squared to the minus 4. And then there's an exponential suppression outside the central region. The total mass of the object, or the axion star, is given by this expression, and it has a half mass radius that is roughly 1. And if you make use of these rescaling symmetries, you can show that the combination of the axion star mass and its radius, the product of the axion star mass and its radius, is actually constant. So no matter how I rescale my solution to get axion stars of different masses, this combination remains fixed in terms of the axion mass. And then just to complete the list of properties, the central density of this axion star is this rescaling parameter squared m squared over 4 pi g equal to say some number of order. Here I'm ignoring some numerical factors, but they're independent of alpha and they don't matter too much. Okay, just to finish the sort of setup of the axion star solutions, let me return to the issue of whether Newtonian gravity is actually a good approximation. So you can estimate when general relativity might be important by comparing the radius of an axion star with its Schwarzschild radius of the corresponding mass. So if we create the expression for the radius of an axion star, for then after a bit of work you see that actually only axion stars corresponding to this rescale parameter alpha being much less than 1 are non-relativistic. But this is completely fine. We've just used this, let's say, starting solution to find one of the solutions in the family of axion stars. And in reality, the stars that we'll care about cosmologically correspond to taking our original solution and rescaling it to much larger radiuses, which means that they're much further from being black holes. Any questions on this? Yep. In terms of, so I think probably no, because it's not topological. It's more that it's just, I guess the way I would understand it typically is that once you get these minus signs consistent, the binding energy of the axion star means that the energy per unit mass is smaller than if I had just the axions dispersed. And given that, it's stable against fragmentation, just like the cue-ball solution is. Yeah. Good. Any other questions? Okay, so a bit more interpretation is we can think of this axion star as just being some bound configuration of many different axions. But the kind of interesting point here is that if I just put a load of particles in some gravitational potential, then you would expect them to collapse down, and the only thing that would support them would be any angular momentum that they started with. So you know that in typical dark matter models, the galaxy is of finite size and not just collapsed down to a black hole because it has some angular momentum. In contrast, what is happening with the axion star solution is that actually in some sense it's the uncertainty principle or the wave-like nature of the axions that is preventing further collapse. To make this slightly more precise, If you calculate the de Broglie wavelength of the axions inside an axion star, one over mv, then this is exactly comparable to the radius of the axion star. If you like, there's no way of squeezing these axions closer together because of something a bit like an uncertainty principle. So in some ways, really, it's a coherent, well, let me not speculate too much on that. So then the natural question is, why are these axion stars interesting? I mean, there's some solution of some Schrödinger-Passon equation, but there's many such solutions. And for me, the reason that these are potentially interesting is that they inevitably form in the real universe if dark matter is an ultralight axion. And it's at least somewhat plausible that dark matter is an ultralight axion. So these are things that really would be existing potentially in every galaxy and every dwarf galaxy in the universe. Let me consider the pre-inflationary scenario. So this is the situation where the symmetry that gives rise to an axion is never restored after inflation. So we don't get it. Yep. Yes, so usually I'll be thinking really small, like 10 to the minus 20 electron volts, somewhere in this kind of region. We'll see the exact scaling in a minute. So in the pre-inflationary scenario, we never restore the symmetry that gives rise to the axion. We never get these strings or domain walls. And the only way that I produce dark matter axions is by misalignment. This is a production mechanism that is inevitable. There's no way of getting rid of it. If I have such an axion in my theory, I will get at least some dark matter production by these kind of dynamics. I won't go through the details of the calculation, but the present day relic abundance of axions produced by misalignment is roughly 0.1. Then there's some dependence on the axion decay constant, which is basically the scale of the U1 symmetry breaking that gives rise to the axion. And let me think in sort of string theory, fundamental string theory kind of motivated terms. So if I normalize FA to, say, 10 to the 17 GeV, then I get this dependence. And let me normalize to 10 to the minus 22 electron volts. So indeed I get, if I want such an axion to comprise the majority of the dark matter, picking FA somewhere roughly near the Planck scale and picking MA really very small gives me the right abundance. Then the corresponding de Broglie wavelength of such axions is enormous, at least for these kind of normalization, these kind of values. So it turns out to be kiloparsecs. And then normalizing the velocity of the axions relative to the typical velocity dispersion in the galaxy today. Maybe since I guess lots of people are particle physicists, do you have some impression of what a kiloparsec distance is? Okay. If anyone doesn't know, it's big. This is the compared to the LHC. So in some ways, this is actually quite cool. Usually you would think of dark matter as being some WIMP or something that's just a particle floating around. Here we're saying we've got a dark matter candidate that is wave-like, and effectively the wavelength in the present day universe is absolutely enormous. A reasonable expectation is that actually I can't make this de Broglie wavelength much larger than the scale of the system that I want the axion dark matter to be in. Otherwise, I simply can't make it self-gravitate and reproduce the observed features of like dark matter dominated dwarf spheroidals and things like this. So in particular, if I have, say I look at roughly the smallest objects that we really know are dark matter dominated, they have sizes of order kiloparsec, they have masses of order 10 to the 9 solar masses, and that corresponds to requiring that the axion mass is roughly bigger than, say, 10 to the minus 22 electron volts. Given that we know that the size of an axion star is roughly equal to the de Broglie wavelength on the solution, it's already kind of plausible that if we tried to build some galaxy where this is not too much smaller than the size of the galaxy, actually what will sit at the center of the galaxy is an axion star rather than just a normal dark matter configuration. On the other hand, you might say, well, we don't know whether this axion star solution is reached. It is the lowest energy solution, but perhaps in the real universe we just have these axions floating around following a normal kind of dark matter halo with angular momentum being important rather than this wave pressure. The interesting thing is you can calculate, or at least estimate, the time scale that it will take for, if I start off with some axions floating around a galaxy, an axion star to form. So this is typically called the condensation time. Let me maybe just give a brief outline of how this calculation goes so you can see schematically the assumptions that are going in, and I'll leave the details of the actual calculation to an appendix. The full cosmological dynamics of starting with some dark matter axions and evolving forward as overdensities grow and collapse is complicated. It's all nonlinear dynamics with gravitational collapse. Instead, let me just consider some idealized situation where I have axion waves in some box of finite size. Total energy density of the axions, let me call rho halo, and let me suppose that these axion waves are in some finite volume V, which is roughly L halo cubed. So this is supposed to represent, if I imagine my full galaxy is some finite size thing and I have my axion waves moving around. And I can also assume that the typical momentum of these axion waves, we call it P halo, such that the velocity is over the axion mass. Since I'm imagining this to be happening within a galaxy, I can ignore the expansion of space. This is decoupled from Hubble flow. And it's always, in realistic situations, a good approximation that the energy of each mode is just given by the usual dispersion relation. And just to simplify the calculation, let me assume that the size of the halo is at least somewhat bigger than the de Broglie wavelength. So now we start off with this situation, and let me say that initially my axion waves have some distribution of momenta that maybe follows a Maxwell-Boltzmann distribution. This seems kind of reasonable. And it's reasonable to think that the timescale on which an axion star will form is related to the timescale on which the occupation number of different modes changes. In particular, in order to form an axion star, I need to scatter the waves into low momentum states. It actually turns out that if you look at the axion star solution, it has extremely small momentum of the waves. Effectively, I've made the momentum as small as I possibly can. So the outline of the calculation, of the scattering calculation, is we want to start with two waves, let's say with momentum k and p, and we want to scatter them into two different momenta, q and l, one of which will have much smaller momentum than the other, effectively building up momentum modes into the axion star solution. Maybe it's worth emphasizing this is a classical field theory calculation. All of these modes have huge occupation numbers throughout, so it's not like usual scattering and particle colliders. It's really classical field theory scattering. So in this in particular, I'm making some kind of momentum, some just Fourier decomposition into psi is, okay, normalization factor that doesn't matter too much. And as usual, summing over momentum modes. It's minus I k dot x. T. There's a bit of a subtlety with scattering by gravity that, of course, gravity is long range, which means that in principle, most of the interactions are long distance, but as you go to longer distance, the momentum transfer gets smaller and smaller. In fact, this is part of the reason that I had to put my system in a finite box. But at least ignoring that slight complication, I can write down a Hamiltonian for this classical scattering. Summing over incoming and outgoing momentum modes, imposing momentum conservation. So this corresponds to some momentum changing, well, some process that conserves the total momentum but changes the momentum of the individual modes while still preserving the axion number density. And this object T, which controls the scattering rate, L, has this kind of form. So I'm not explaining this in complete detail, but it's sort of the form you'd expect for the scattering by a massless graviton. Okay, next step is to define, rather than working in terms of the original field, psi, let me define mode occupation numbers. So we write psi of k is equal to k. This is just a change of variables, but it's convenient so that now these quantities f of k satisfy k. t squared, so it tells me how many quanta, if you like, are in the mode with momentum k. So now I'm going to skip a bunch of steps that are in the appendix, but I think the result that comes out will be hopefully somewhat believable. The rate of change of a mode occupation number due to this kind of scattering is given by called d cubed p cubed cubed. Sorry. And then some energy and momentum conserving delta functions. I don't think the exact details of this derivation are the most important thing, so don't worry. Of course, I don't expect you should immediately see how to get from this kind of scattering Hamiltonian to this kind of expression. It takes quite a bit of work. But the key, yeah. No, good point. Yeah, so here, just to stay completely general for the form of the Hamiltonian, I've allowed it to depend on both the incoming and the outgoing momenta as like a general interaction would. In practice, for a gravitational interaction, all that matters for tau is the momentum of the exchanged graviton, if you like. So that just depends on only two of them, or equivalently, I could write it in terms of the other two modes. So having the four, in some ways, these indices I didn't need to include. They have no dependence on the right-hand side. But yeah, exactly. So the P. Yeah, exactly. So I've gone from QL to LQ there, and one way to interpret this is that if I want to have scattering, imagine I want to know how fast the mode with occupation mode K changes. I could either have some scattering where, say, K comes out like this, or I could have the cross diagram where, say, let me draw it like this, where that's K coming out there, so it changes the, yeah. Good question. Any other questions? Yep. 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 Good question. So, okay, to repeat the question, these being formed by misalignment, like these inherit normal adiabatic fluctuations. Indeed, they would have to, otherwise the whole theory would be completely ruled out by observations. Here I'm thinking of the dynamics at extremely late times once these initial adiabatic fluctuations have already collapsed down into galaxies so that the horizon is huge compared to everything else, and we're just thinking of this is just my galaxy way inside the Hubble horizon, and I don't need to worry about anything like that. But indeed, it's true that actually what forms this galaxy in the first place is the adiabatic fluctuations that are already there. So we're kind of thinking, taking the perspective, somehow the galaxy is already formed, we've got this gas of axions floating around, what happens next? Any other? Yep. No. Yes. Short answer, yes. They probably also have some initial angular momentum merge into a sort of excited axion star that then chucks off some axions to spatial infinity. But most of what you get left over with would be a larger one sat in the center. And indeed, this can actually be cosmologically relevant. You know that the Milky Way is constantly merging with constantly on galactic time, cosmological timescales, not on our timescales, merging with other smaller objects. Indeed, this is how hierarchical structure formation proceeds. Smaller and smaller things merge together. And in this process, axion stars will merge to make a bigger one. This is, again, some very simplified situation to give an idea of the timescales rather than what would actually happen. Yeah. Any other questions? No. Okay, good. So schematically, this is the rate of change of the occupation number. We're integrating over, aside from k, these incoming and other outgoing momenta, also allowing that k could be one of the incoming ones, in which case we'd lose occupation number. And the way that the indices appear on these taus corresponds to these different possibilities for changing the occupation number of k. The other thing that's kind of important are these factors of fk on the right-hand side. These come about effectively by the analog of Bose enhancement. So if I have some occupation number already, then it increases the rate of scattering. The minus sign is then subtracting off like the forward process in which I produce some k from the backwards process where some momentum k gets absorbed in the scattering. This is fine and it's true, but it's not very useful for working out if an axion star actually forms because we want to actually know the rate. So let me do some dramatic approximations of just approximate d cubed p over 2 pi cubed goes to roughly the initial momentum of the axions in the halo cubed. The occupation numbers we're going to say go to be roughly the initial occupation numbers of the modes in the halo, so rho halo divided by m lambda de Broglie cubed, which is the same thing as rho halo over m to the 4 v halo cubed. If this isn't familiar, the justification for this is that the number of modes in the halo, just because it's a finite box, is schematically L halo cubed over lambda de Broglie cubed. And that means that the occupation per mode, and we have that the occupation is roughly number density of particles times size of the halo cubed. So this is the total number of So the total number of axions in the halo is given by this expression. The number of modes is given by this expression. So the number of axions per mode is given by that divided by that, which should hopefully be that thing. Yep. Then the final part, which is actually maybe the most dodgy of these approximations, is I'm going to approximate tau is roughly gm squared. And let me assume that the typical momentum exchange in a scattering process is given by the momentum of the halo. So that becomes squared. Then I can estimate that the time to form an axion star is going to be roughly f dot over f. So this is telling me when the occupation number of a given mode has changed by an order 1 amount. Well, when this is equal to 1, then occupation number will have changed by an order 1 amount. Putting those approximations into that expression, we get out that this is equal to some number which is conventionally written as, let me just match the existing literature by putting in factors of pi's and so on that don't really matter, where b is some numerical factor, v halo to the 6 over g squared. Some number that isn't particularly crucial, but then all of the dependence, actually, if you go through plugging all of these approximations into that expression, comes out to this expression. And actually the only thing that I missed by these kind of very broad approximations is there's an additional factor of 1 over logarithm size of the halo, mv halo. In some ways, this logarithm comes about just because, as I was mentioning, gravity is long range. You get something that, if you've ever studied plasma physics, looks like what people call there a Coulomb logarithm. In particular, scattering is actually dominated by very low momentum scattering rather than being dominated by typical momentum of the halo, as I wrote here. But in reality, this number being a logarithm is maybe 10, maybe 100, but not much larger than that. This means that the typical formation time for an axion star at the center of a galaxy is something like 10 years times 2 electron volts cubed. Maybe normalize the halo velocity to, I don't know, say a typical value, 10 kilometers minus 1. And I'll normalize the density of the halo to m solar per parsec cubed. The age of the galaxy is certainly much longer than 10 years. So this means that provided the axion mass in this ultralight scenario is not too large, say as long as it's bigger than 10 to the minus 19 electron volts or something of that order, maybe even slightly smaller, an axion star would have formed, one of these objects would have formed at the center of the galaxy before the present day. And indeed, if you do numerical simulations of this type of system, that is indeed what people find out is the case. These are the timescales involved. So this is potentially quite interesting, and in some ways would be a pretty distinctive signal of this kind of ultralight axion dark matter compared to, say, wave-like, compared to normal particle-like dark matter. One thing I haven't yet told you is how big this axion star is. It wouldn't be particularly interesting if actually I form an axion star, but it's just very slightly bigger than the supermassive black hole at the center of the galaxy. Would never really be very hard to observe it. There is actually a prediction for how large axion stars should be, their masses and their sizes, as a function of the halo that they're embedded in. These are not, I think, completely understood yet, but with some combination of simulations and some analytic arguments, there's some reasonable evidence. So let me just tell you what was proposed from looking at simulation results, and then I'll give some better justification for it. So from numerical simulations, people claimed that the mass of the axion star in the core of a given dark matter halo was given by absolute value of the, here, C means star. I could change this, but core H. So the picture is I have my large galaxy, and inside at the center I have some axion star at the core. E halo over mass of the halo So when this was first done, this was just postulated as some, well, in some sense, observational from simulations relation that looked a bit mysterious. We can actually put it into a more useful form that gives a bit more physical understanding by using what I showed you before, the scaling of our basic axion star solution, which tells us that if I start with my basic solution and I rescale it by this amount alpha, the energy of the star is given by alpha cubed m Planck squared over m, and the mass of the star is given by alpha Then, using that relation, we see that for any given axion star solution, we have that its energy, absolute value, just to avoid minus signs, over its mass is equal to alpha squared. And what the claimed relationship between the core and the halo reduces down to is the statement that the energy of the axion star divided by its mass is equal to the energy of the halo divided by the mass of the halo. In more physically useful terms, if we say that the systems all are virialized, then the energy per unit mass is roughly the velocity, the virial velocity squared. And our claim is that the virial velocity of the axion star is equal to the virial velocity of the surrounding halo. Actually, this is kind of reasonable. So if we think of our collection of waves, it's telling us that if the de Broglie wavelength of the axions in the halo is given by some size lambda de Broglie, then what I'm going to form is an axion star that has a corresponding size of lambda de Broglie. And then if the star gains further mass, it will shrink, it will get smaller than the de Broglie wavelength of the axions in the surrounding halo. And at that point, it becomes increasingly hard for this scattering process to transfer additional axions onto this core. So in some ways, this is would be the end point of the growth of the axion star. This is interesting. It means that for typical values of the axion mass, if you go away and you look up the numbers for the Milky Way, this predicts that we would actually have a really quite large axion star at the center of the galaxy, at least for axion masses of 10 to the minus 20 electron volts, 10 to the minus 20 electron volt, 22 say. Okay, so this has been kind of schematic. In part, that's because the scattering calculation is quite complicated, but at least for this later part, it's also schematic just because this is not fully known. It's still an area that people are working on. Observationally, certainly this star would matter. You could imagine something like looking at the galactic rotation curve looking at the rotation curves of stars in the galactic center. We already saw that the profile of a star in its center looks something like this, with a flat region where this is of order lambda de Broglie, just like everything else. Whereas if you've looked at normal simulations of cold dark matter, you'll know that you typically get out something like an NFW profile with a very sharp power law-like divergence for the dark matter density in the galactic center. So this could be distinguished. You could also imagine kind of interesting effects if this axion was coupled to photons, because unlike normal, let's say, dark matter models, here the dark matter is really one single coherent field over the entirety of the inside of the galaxy. I'm not sure if it's completely accurate to call this like quantum effects, but it's at least some extremely large occupation number that would potentially change the dynamics. Any questions on this stuff? Yep. Yeah. So, okay, so I guess there's two things here. So this formation time is actually depending on MA. So, the mass of the star. Yes. So indeed, the formation process is complicated. What I think is seen typically in simulations is that you kind of watch these waves fluctuating for a long time. Suddenly you start getting to a star that is an object that is sufficiently large that is actually stable. And then once you happen to have one of these fluctuations that is big enough, it then very quickly grows up to become like a stable axion star. If you like, to make a connection with what I'll talk about tomorrow, for finite temperature phase transitions, for a phase transition at finite temperature by thermal fluctuations, you look at the system, there's complicated thermal fluctuations, occasionally you will actually get some fluctuation that is large enough to be a so-called Sphaleron configuration that takes you above some critical point when then the phase transition proceeds. I think the situation is probably pretty similar here, that the axion waves are constantly interacting and fluctuating. Occasionally you'll get a fluctuation that is large enough to become a stable axion star, and then you'll very quickly accrete up to this kind of critical core halo relation, and then it will survive. The other complication is, as I sort of alluded to, in a realistic situation, the galaxy is collapsing, dark matter is becoming bound from some small initial overdensity at the same time that the axion star would be forming. So this kind of cartoon picture of just waves floating around and eventually forming an axion star probably isn't completely accurate, but it gives us some handle, and it gives us at least some convincing evidence that these things would exist cosmologically. Any other questions? Okay, if not, I think I'll stop 2 minutes early. Tomorrow we'll go on to vacuum decay and instantons and things like that from maybe a slightly different perspective to what you have seen so far. Thanks.